I'm going to start now the recording of the session. Um, and so what I want to start is with questions that you might have. The first thing is just a reminder that, yeah, the exam is same as last week. We will have the exam access in Canvas at 6 p.m. I'm expecting you to be there on the Zoom call at 6 p.m. and um, and then you'll have some multiple selection questions, and then you'll have some open questions that are going to be answered in Grayscope free response. So I got a question. There will be more short answer questions than the four that were on the last week. I'll say it's like half and half. I'll say the exam is half and half. There's a good chance on this test to actually showcase your knowledge of what you're doing. And so you're gonna have like half of the questions will be so you can answer in Grayscope and free response. But at the same time, you have a good chunk of multiple selections. I think it's pretty balanced. The exam again is like designed for you to be completed like in an hour if you're having a good pace, but I'll be providing like at least hour and a half just to account for anything that might be extra times in terms of signing up via honor lock or anything that can take extra accommodations in that sense. Okay, so I see that there's a couple people here on the session. Noah, do you have any questions for me?
Are we gonna have to simplify written response questions for like derivatives and stuff?
Um, it depends. My answer will be not really. The only thing that you will have to do some sort of calculation that might be worth simplifying is if you're doing like a um, equation of the tangent line, where,
Okay.
for example, you calculate a derivative and you got to plug in a point. And so when you plug in that point, then you have a bunch of numbers that you need to multiply and subtract and divide. That might be something that you do need to simplify. But if we're talking about algebraic simplification, not really. If
Okay.
I ask you, let's say for a quotient rule, let's say something like, let me see if I can write here. Let's say f of x is equals like, let me give you something complicated. Something like x squared plus 3x squared plus sine of x over, let's say a e to the x plus log of x plus x. Let's say we have this, and I'm asking you to do the derivative of this one. So this is just a quotient rule. And so we can do quotient rule with the rules. Derivative of the first one, 2x plus, well, I should done this a different exponent. Let me just do 3x to the 3. So it makes sense. So 9x squared, then plus cosine of x. So derivative of the first one, then times the second one with no derivatives, and then minus, and then at that point, I gotta move this a little bit. Oh. Okay. And then at this point, this one, no derivatives. And then the derivative of this one, which will be e to the x plus 1 over x plus 1. And you can see this is a mess in terms of simplification. So I don't want you simplifying that. If you want to leave it here in the next point, once that I do the bottom square, that's it. That's fine. That's completely fine. So this
Okay.
needs no simplification.
Okay.
Now, if you're doing something like, for example, this is number one. Number two, find the tangent line x equals 1 for f of x equals, I don't know, like x squared times log of x. So this one might need you to actually find out those things. Like for example, f of 1 is clearly going to be 0, just because log of 1 is 0. And this is my y0 point, where my x0 is going to be, of course, 1. Now my f prime is going to be 2x log of x plus x squared times 1 over x. And so in this one, you might want to simplify before actually plugging. So this will be 2x log of x plus actually x. So
Okay.
that will be the simplification. And then once that you're at this point, then you're gonna say, well, then what is f of prime of 1, which is gonna be my slope? Log of 1 again makes a 0, so this is just gonna be 1. And then you go, oh, my equation is y minus y0, m x minus x0. And so this is y minus 0 equals 1, x minus 1. You know, just because of the need to actually go ahead and simplify. Does that make sense?
Yeah, that makes sense.
All right, any other questions you might have?
Um, let me think. I don't think so though.
It's still gonna be no calculator, right?
Yeah, no calculators.
Okay.
For the most part, you shouldn't need to have calculators at all. The most of the calculations should be like very straightforward, unless you're doing like fractions, which will be a weird case, but nothing that really requires you to do very big calculations.
Okay, I just wanted to make sure because like on the homework I do, I use the calculator just so I don't mess anything up. 'Cause it's really tedious.
Yeah, homeworks do requires that you use calculator, and one of the things that is annoying on the WebAssign is that sometimes you gotta be careful with your number of decimals and that kind of stuff. But no, this one it should be more straightforward.
Okay.
So now that we're going into this, so let me just go ahead and share my screen. And I'm going to go over some of the preparation stuff for tomorrow. Here I just have the usual. So this is the view that you have. You're probably now watching week 4, and so the test is going to be at the very end. So here is the, of course, the Zoom call where you access at 6 p.m. and here's going to be the access for the test, which is going to open tomorrow at test time. Okay. Normally this test has a password, but once that you go into HonorLock automatically will put the password for you, so you don't need to do anything special in there. Okay. And at this point, you probably saw that you have this available. And I'm gonna be making these solutions to this practice problems available once that the session is done, together with the recording here. All right, so let me go over some of the practice problems. I have a very lengthy practice problem part for this exam. We have a huge amount of things, so I don't anticipate that I will be able to cover everything. But it would be good that you take a look as well to what I'm doing in case you have a particular suggestion about the type of question that I should address. Like I said, I have 26 pages of things here to show, so I'm not gonna be able to show everything. My recommendation is, if you have a question in particular that I didn't cover, just make sure that you go over the solutions that will be available in the module of test 2 preparations. But otherwise, in the meantime, for you guys that are in the call, if you have this text practice problems and you want me to go over a particular question, just let me know. So I'm going to start with some of the multiple selection questions here. For example, we have one in terms of the chain rule. So we have that f of x is arcsine of e to the 2x. Of course, this is a chain rule because it's a composition between one function compose another function. And that's what immediately is going to tell you this is a chain rule. So if you recall a little bit about how the definition of the derivative is, the definition of arcsine, the derivative of arcsine is just 1 over the square root of 1 minus x squared. But because we have the chain rule, then we're composing with whatever is inside of the function, which in this case is e to the 2x. So that's why you'll see here that the derivative of arctangent of gx is 1 over the square root of 1 minus gx squared times g prime of x. And then we just got to remember that g of x is e to the 2x. So we just plug that into whatever the space is for where g of x is supposed to go. And remember that the outside derivative is just going to be 2e to the 2x. Okay, so this would be like a standard chain rule question. A similar one will occur in here. We have our arcsine here. Now here we have the arctangent. So a good measure is always to remember what the base derivative is. So for example, the arctangent derivative here is 1 over 1 plus x squared. And then we get to compose with whatever was inside. Here the function, for a function general g of x, this will give me a derivative 1 plus g of x squared times g prime of x. But because of the fact that g is 1 over x, then g prime of x is just going to be minus 1 over x squared. So that's the reason why we follow here. This is step. And then I'm writing first, oh, okay, so once that I plug this 1 over x here, this transform in this complicated expression. Notice that I do simplify in here, but I'm not expecting you to do this. So if you are doing this, you'll be good at this step, step number 2. When we get to understand that you did plug the function that it was composed and that you did find the derivative that it was the derivative of the inside function, you don't need to do all the other steps. If you want to, you can, but you can stop here. Does that make sense? No?
Yeah.
Is that a good example?
Yeah. The only problem I really had was actually on the participation worksheet number 3.
The participation number 3. Okay. Let me go and see. I'm actually going to go and do the solutions to that one later, but let me just see it briefly. So that is this question here, right?
Yeah.
Okay, so this is differentiate this function here. And so the complicated part is that this is a gigantic composition, but you can always treat this as this. Do you see? Regardless of whatever it is. And so what is going to be the derivative of this? Is the same thing times g prime, right?
Okay.
Now let's focus. Let's find out what g is. Now g is what? Oh, is secant of x squared log of base 2 of 3x. So that seems complex as well. But what you can do is you can always do the same thing. So this is too complicated. So now let's call it g is secant of f of x, right? And so what is g prime? Well, g prime is going to be the derivative of secant, which is secant of f of x tangent of f of x. Am I making sense so far?
Yeah.
By f prime of x. And so, of course, then again, what is f of x? Then once that we define what is f of x, then we find f prime. So if we do f prime over here, what is f? F clearly is x squared log of 2 of 3x. So that's a product rule now. And so what is the derivative of this? Well, the derivative of x squared is 2x times log base 2 of 3x plus x squared. And then now we need the derivative of log of base 2 of 3 of x. So the derivative of a log is always 1 over log of the base. So 1 over log of 2, right? Times 1 over whatever is inside. Right? So 1, 3x. And as because we have a chain rule here, we have a small tree, then that's going to come into play here. And it's going to be multiplying here at 3. So if I simplify this a bit, notice that this becomes 2x log of 2, 3x. And then this 3 goes away, this x goes away, and then this becomes x over log of 2 of 3x. Does that make sense?
Yeah.
Okay, so now that we got the final one, then we go back. And then it's going to be a little tedious, but then we write, okay, y prime is 3 to the horrible secant x squared log of 3 of 3x. And then times g prime. But who's g prime? Oh, is secant of x squared log base 2 of 3x. Tangent x squared log base 2 of 3x. And then I gotta multiply by f prime, which is all this. So it's very long, but that is the way that you do it. And as always, if you can determine that this is a composition, you can always break this apart in steps. So you remove the complication. You see?
Okay.
Okay. So who's M on the chat? By the way, when you go into the Zoom calls, especially on the exam, make sure to have your proper full name and last name, since I'm taking attendance. And so a name will be considered. Okay.
Am I allowed to wear like a backwards hat?
No.
No hats. All right.
Yeah, no hats on the exam. You honor lock should be able to see your full face. Okay, so one of the in the survey of last week, I actually noticed that people were saying that they were concerned about implicit differentiation. So let me go over this particular example to talk about implicit differentiation. So we have here that the slope of the tangent line to the curve x cubed plus 3y plus 2y squared equals 6 at the point 1, 1. And what you got to remember is that this 1, 1 point is x and y. So the first thing is, well, whenever you're doing a derivative and it has x and y implicitly, what does it mean of implicitly? Let's remember that something is implicit if not is not explicit. And what explicit means? Well, explicit means that I can put either x in terms of y or y in terms of x. In this case, it's not easy to put y in terms of x because there's y here. And so it's impossible to factor and to leave a single y in terms of only x. So that's what explicit means. So otherwise, these expressions here are going to be implicit expressions. Also, because we're considering that y depends on x. Y is a function of x, okay? So where is that going to be reflected? Well, that's going to be reflected that we can just take derivatives normally. You can see the derivative of x cubed plus 3y plus 2y squared is 3x squared, like you would normally get to a power. And here we get 3y, and normally the derivative of y will be 1, and that is true as well. That will happen here. But every time that we're taking derivative by y, we multiply by the y dx. Why? Because there's a chain rule there coming in. Y depends of x. So that's why we get this part. Now this 2y squared, then the derivative of this is 4y, which is the outer derivative, and then the inner derivative is just gonna be the y dx, okay? So the normal step then when you're doing implicit derivatives is that you're gonna factor out this the y term, okay? By the way, can you see my cursor on the screen at this point?
Yeah.
Okay. All right, so once we are at this point, then what we want to do is we want to factor out the dy dx. So we move whatever doesn't have the y dx for the other side. So we get 3 dy dx plus 4y dy dx equals minus 3x squared. Then we can factor here the dy dx, and we get something like, oh, the y dx is equals minus 3x squared divided 3 plus 4y. Now, that's fine, and that's fine because we have a point 1, 1, and so that's giving me coordinates x and y. So to find the slope, because remember we're trying to find a tangent line, and a tangent line is done with the slope and point. So I already have the point. The point is 1, 1. So to find the slope, I need the derivative, and I just plug the 1, 1 point here. So plugging that in there, I get minus 3, 1 squared over 3 times 1 plus 4 times 1, and that's going to give me minus 3 over 7. So that will be the slope of the tangent line at this point. If the question is not asking you for the slope, but it's asking you for the line, then you'll need to complete with the equation of the line given this point and given this slope, okay? Now, a lot of questions can come in this sense. And a big thing of what is going to come in this exam is going to be a test of you knowing how to do chain rule, you knowing how to do implicit differentiation, you knowing how to do logarithmic differentiation. So sometimes logarithmic differentiation will come like this, where you have the derivative of a log. And what you gotta remember is that this is just log of a function. So by chain rule, this is just gonna be 1 over the function times the derivative of the function inside. So that's precisely what we have here. F of x log of x to the 4 times cosine of x. So f prime is just gonna be 1 over the inside function, which is x to the 4 cosine of x. And then we're going to multiply by the inner derivative, which is going to be whatever the derivative of x to the 4 cosine of x is. And notice that I just leave this set up in here. And then after that, we're going to find out who the inner derivative is. In this case, this is a product rule. So we get that this is 4x cubed times cosine of x minus x to the 4 sine of x. And once that we get there, again, this will be a good point to stop. You don't have to go further. If you want to, though, then you can continue simplifying, but just make sure that your simplification are actually correct. Sometimes you can also take advantage with logs of the properties of the log. So for example, you see here, f of x can be considered in a second way, and it's just split this by properties of the derivative. The derivative of the log of a product is just the sum of the log of each of the parts inside. So this will be log of x to the 4 plus log of cos. Now, the good thing about that is that it simplifies so much everything. Like also we can use the property of the power. Log of x to the 4 is the same that 4 log of x. And so this is simplified to 2 single logs. Notice that we're using properties of the logs in here. Log of f times n is equals of log of m plus log of n. And log of the power m to the r is equals r log of m. Now, notice that with this simplification, I just do 4 over x at f prime. And this will be 1 over cosine times the derivative of cosine, which will be minus sine. And there's where we got this 4x minus sine over cosine, or 4 over x minus tangent. So essentially, you see that you're going to get to the same point. Okay. Now, when you're trying to find multiple selection questions, though, that might take you or might force you to simplify a little bit as well, because you're not seeing anything. Like you reach to this point, you might be forced to simplify because you don't see anything of this magnitude in the options. Okay. So that's something that you might want to take into account. So in some scenarios, you will need to do this simplification just to contrast with the options that you're being given. In a fair response scenario, you can just get to this point and you'll be fine. Okay. So that'll be my contrast there in terms of what is needed for you in the exam. Now, let me jump to some questions of the chapter 4. So in chapter 4, we're doing optimization, and optimization is about maximums and minimums. And there are 2 scenarios where you can find maximums and minimums. One of them is in a closed interval, and the other one is just a general interval. In this scenario here, we have the absolute maximum value for the function x to the 4 minus 4x to the 3 plus 4x squared plus 1 on the interval minus 1 to 1. So what are the usual steps for maximizing? And so just, by the way, let me just remove this from here. I'll come back to this later. So normally, when you're trying to find max or mins, you have 2 options. You are going into an interval, AB, or you're in a general domain. They both have some similarities on the fact that you gotta find out f prime of x equals 0 to find critical points. So critical points. But then what happens is that in the general domain, you do a sign chart. This is a step 1. And then a step 2, you do a sign chart to check where are the maximums and minimums. So for example, you have C, D are the critical points. Then you start checking how the function derivative behaves around these points. And so you start picking some numbers here. And so you say, well, it's going to increase here, then it decreases here, then it increases here, for example. And so if it's first increasing and then decreasing, is doing something like this in the function, and x equals c is a maximum. And if it's doing something like this, like what it does in D, it's doing this with the function. And so here x equals d is a minimum. And this is what you do for a general domain. Okay. However, when you have an interval, what you do is you find the critical points. And so let's say that f prime of c and f prime of d are 0. But c is the only one on the interval AB. Okay. So then later what you have to do here is you forget about D. You don't care about this one because D does not belong in here. Okay, so I'm not interested in this one. And then the next thing that you gotta do is you gotta compare. You compare f of a, f of c, and f of b. And the largest is the max. And of course, the smallest is the min. Okay, this is the general idea for finding maximums or minimums here. Okay, so let's see that in place. We have this function x to the 4 minus 4x to the 3 plus 4x squared plus 1 and the interval minus 1 to 1. First thing is we take derivative. The derivative of this is going to be 4x cubed minus 12x squared plus ax. We can actually factor 4x out of this, and we're going to get 4x factor of x squared minus 3x plus 2. And then you factor this out, and this is going to be 4x times x minus 1 times x minus 2 equals 0. This is a fairly complicated example because it's going to give you multiple critical points. In here, we have 3 critical points only coming out of here. And so we are going to have to not only check for critical points, but for the points on the extreme of the interval. X equals 2 does not belong to this interval, so we don't care. X equals 1 does, and x equals 0 does. So now we're interested in evaluating 0, 1, and minus 1. And that's it. And then we check, okay, so f of 0, which we plug in this function, the original function, is 1. F of 1 is 2, and f of minus 1 is 10. So clearly, 0, or in 0, we have a minimum point, and then minus 1, we have a maximum point. Okay, we have an absolute maximum, and x equals minus 1. And then our minimum here just will occur at 0. Does that make sense?
Yeah.
All right. All right, so now for contrast, let me jump on this because this is L'Hopital's. I don't want to enter yet on this. So now let me jump to another. Yeah, so for example, this one. This one is going to help me find the maximum, but of course, when we're working in general, then we can find much more than that. We can find where the increases, where it decreases, whereas concave up, concave down. So for this function, e to the minus x squared, we're first going to find the derivative, which is going to be minus 2x e to the minus x squared. And so we check when this is going to become equal 0, and that will only happen here at x equals 0, since the exponential is always positive, so we're not going to get much more than that. Now, this is only going to give me a critical point, and so there's a stark contrast with what we had before. We can only split the real line into intervals here to check what is the behavior. We do from minus infinity to 0 and 0 to infinity. And so this is like my sign chart. These are the 2 intervals that I have. And I'm going to pick a test value in each of those. And I'm going to find the sign of f prime in each of those intervals. So I can see plug in now in f prime, plug in minus 1. I can check that's going to be positive. And so because it's positive, it's going to be increasing. And I can see that after, I can pick a number like 1, and it's going to be negative here, minus 2x times e to the minus x squared in 1. It produces minus 2 over e, and that's less than 0, so it's decreasing. So as you can see here, this is increasing, and then it decreases, so x equals 0 is actually going to be a maximum. And we have that, we have increasing function here and a decreasing function here. Remember, the critical points are points where increasing and decreasing values change. Now, another thing that we can look for in here is concavity or inflection points first, if you will. So the critical points are where f prime is equal 0, but the inflection points are potentially going to occur where f2 prime is equal 0 of does not exist. In this case, that might even be the case because we have something that is potentially dividing, although we can take this as a product rule, if you will. F2 prime here, when we take derivative of this, is just like minus 2 e to the minus x squared. Remember, we're taking the derivative of minus 2x, so that's just minus 2. And then when we do the derivative of e to the minus x squared, that's going to give me again e to the minus x squared times minus 2x. So I end up having that the second derivative is going to be 2 e to the minus x squared times minus 1 plus 2x squared. Now, again, the exponential cannot be 0, but this term here can be 0. This is a polynomial. We have 2x squared minus 1 equals 0. That means that f2 prime is going to be 0 at x equals plus or minus 1 over square root of 2. Okay? And so that's going to give me a split of the real line in 3 pieces, from minus infinity to minus the square root of 2 over 2, from minus the square root of 2 over 2 to square root of 2 over 2, and from square root of 2 over 2 to infinity. Now we pick a number in each of this sub-intervals, and we check what is the sign for the second derivative. And so where f2 prime is positive, we have that f is concave upward, and where it's negative, we have that it's concave downward. And so because of that, with that arrangement, we can see that in the interval minus infinity to minus the square root of 2 over 2, we have concavity upward, then it changed to be concavity downward, and then concavity upward in the last interval. Okay. All right, any questions here, guys? Or just give me a thumbs up if everything is good so far. All right. All right. So for the most part, and like getting back here, remember that the topics that are included on these exams is everything from weeks 3 and 4, which is pretty much a lot. We have implicit differentiation, chain rule that we covered somehow, trigonometric functions, logarithmic and inverse trigonometric functions, and then we're jumping to linearization, linear approximation, maximums and means, mean value theorem, and curve sketching. Okay. So now let's go to another different type of thing. Where do we have maximums and minimums? Yeah, let me pick another exercise. Or do you have any suggestions in something that you want me to do?
Could you do 4.2 mean value theorem?
But any particular question, or you're talking about like the section?
Just like examples of it. That's the only topic I'm really struggling with. Everything else is pretty clear.
Okay, so for example, this is a good question for it. Essentially, the mean value theorem is about finding a specific value for the derivative. Notice that we have this type of a statement. So we have f of 1 is 1, f of 3 is 5. So there is going to be a number c on the interval 1 to 3, so that f prime of c is equals 2. So if we want to verify this type of a statement, what we always do is, well, let's check if that makes sense. F is differentiable on that interval minus infinity to infinity. So I want to check what happened with the difference between f of 3 minus f of 1 over 3 minus 1. And notice that I have some values in here. I have f of 1 is 1, f of 3 is 5, so I can actually calculate what this is. We're going to have that f prime of c at some point gotta be this 2, 5 minus 1, which is 4 over 3 minus 1. So it's 4 over 2 is 2. And so this is just pretty much from the definition saying what the mean value theorem is. So the hypothesis is that you have continuity and you have differentiability in a given interval. And so you're able to find a number that is a certain particular amount. Okay. What the other statement that is true also here is 3, which is saying if f of 1 is 1 and f prime of x is less than 2 for 1 between 1 and 3, then f of 3 is minus 3. And so this is something that we can probably look on the board to see how will we go about it. So this is saying f of 1 is equals 1 and f prime of x is less than minus 2. Then I want that f of 3 is less than minus 3. Okay. Notice that I already have a hypothesis and it's this and this, and I want to know if this is true. Okay. So what is the mean value theorem saying? Well, the mean value theorem is saying, well, f of 3 minus f of 1 over 3 minus 1 should be equals to a certain value f prime of x with and that x should belong to the interval 1 to 3. Okay. But notice that we have information about f prime of x. We know that this is always less than 2. So we have this inequality. So what this is saying is, well, I have that f of 1 is 1. So f of 3 minus 1 over 2 is less than minus 2. So can I solve for this? So f of 3 minus 1 is less than, multiply both sides by 2, minus 4. And then f of 3 is going to be less than minus 3. So this will be true. Does that make sense?
Yeah, and then the last question I had was for graphs increasing and decreasing using a function. So you don't have to take the second derivative to determine whether or not it's increasing or decreasing. That's just specifically for concave down, concave up.
Yeah, so first derivative is what it tells you if it's increasing, decreasing. First derivative positive implies f increases. First derivative negative implies f decreases.
Okay.
F to prime negative implies that f is concave down. F to prime positive implies that f is concave up. Does that make sense?
Yeah, that helps a lot.
Yeah, so this is the summary, but you can also go the other way around. So you can think of this as this. So if you have information on f, you can kind of guess what the behavior of f prime is. If you know that f is increasing, then you should know that the derivative is positive there.
Okay.
That's like the backward of it. Like for example here, well, it depends. Like there are multiple type of questions that you can go with this. We have this graph in here. And let me actually try and get it to my board. Yeah, no. Okay, this graph, and I want to know which one of the following things is true. So I have the answers in there, but let's check why those things are happening. Okay, this says which of the following statement is true? F is decreasing on the interval minus infinity 1. So this is misleading. This part here is misleading because you can see this function and is decreasing. The problem is that this is not the function. This is the derivative. Okay. You got to remember that if f is decreasing, then f prime is negative. F
Okay.
prime is not negative here. You see?
Yeah.
Now, so this is the first derivative. First derivative. So the first derivative here, notice, is positive. Okay.
Okay.
So, because f prime here is positive in this interval, it means that f is increasing. And this is from minus infinity to minus 1. I think this is wrong. Because this is asking what if this is true and this is not true. 1 is not true. Okay, so might be wrong. Let's verify. F has an inflection point at x equals 0 and x equals 1. So inflection points are two things. Are points where the concavity is changing. So it's doing something like this, changing from concave up to concave down, or changing from concave down to concave up. Something like this. So these 2 points are points of concavity change. They also, or inflection points, they also are reflected where f2 prime is equal 0. How do you find the points of f2 prime is equal 0? Well, with the derivative, that means that you gotta look where f prime is flat. So for example, here you see there's a flat in 1, there's a flat in 0.
Okay.
And so this number 4 is actually true. There are inflection points in there.
Okay. And then
F, like number 3, says f is concave upward in the interval minus infinity 0. Concave upward. Okay. So to be remembered to be concave upward, according to the definition that we gave here, f2 prime gotta be positive. So what we need to look here is for the derivative of the derivative and see what the sign of this is. But the problem is, notice here, we have that this is almost a line. So if we take the tangent line of it, it's gonna be a negative slope. So because it's a negative slope, then it means that it's gonna be concave down. Okay?
okay.
So we know immediately that this is not true. And then f has a local maximum at x equals -1 and 1. So here is changing from decreasing, because the function, sorry, this is f prime. This is f prime. So the function is increasing. And then after -1 is negative, so it decreases. So -1 has a local maximum, that is true. And then at 1, it's not a local maximum because notice that it's negative. It doesn't change. So although it has a local maximum of -1, it doesn't have a local maximum at 1.
Okay.
Do you have another question?
I just wanted to see the answer to 21.
The answer to 21?
It's another mean value theorem.
Okay, so it says let f of x be square root of x, find a number that satisfies the numbers of the mean value theorem. So this is a straightforward mean value theorem. So what you do is, well, you set up what is f of 64 minus f of 9 over 64 minus 9, right? And this is something that you can do because the square root of x is continuous and it's going to be differentiable, especially in this interval. So then you calculate what is f of 64, which is the square root of 64, which is 8, which is what is f of 9, which is going to be 3. And below, divide by 64 minus 9. And so this means that this is going to give me 1 over 11. So it gotta exist a certain point such that f prime of c is equals 1 over 11. Okay?
Okay, yeah.
So
I
for
had.
sure, yeah.
Here, you go ahead.
Go ahead.
So I had the interval right, like the average rate of change and everything. I just made like a algebraic mistake when setting it equal to it. I set it equal to f, not f prime.
Yeah. Yeah, it's f prime. You gotta be careful not confusing maybe the mean value theorem with the intermediate value theorem.
Yeah.
Okay. All right. And to find out what that specific value is, though, then you gotta make the derivative. So f prime is just gonna be 1 over 2 squared of x. And so you're setting up pretty much 1 over 2 squared of c to be 1 over 11. And then you solve for c in there. And then you're going to find out that this c is like 121 over 4, which is probably a number between 9 and 64. If it were a 120, it will be like 30. So this is probably 30 something, which is lies between 9 and 64.
Okay.
All right. Any other question? No?
I feel pretty good about everything else, so no.
Okay. What about M? Which
I think I understand everything.
okay, please remember for tomorrow's call to just put your full name and Zoom, okay?
Okay.
All right. So one of the last thing that I'll address to just jump around all the topics is the linear approximation. Linear approximation are this type of estimate this function, and what you gotta remember is that when you're estimating, you're using the tangent line to estimate the value of the function. And because when you're close, then their values are so close, there's a little error between them, is that you can make this estimation. So to be able to create a linear approximation, we first need to think of a function that relates to that. So for example, we have cube root of 8.2. I want to estimate that. So it's natural to think, hey, my function is going to be cube root of x. and I'm gonna be estimated close to 8 because I want 8.2. So I'm gonna estimate in 8. Okay. Now, the linear approximation function is the tangent line. So it's given by f of a plus f prime of a times x minus a. Okay, that this is the linear approximation, and it's always going to be the equation of a line. And so therefore, what you should expect from the linear approximation is that it's an equation of a line. And remember, the equations of a line always have the shape y equals mx plus b. Okay, so something like this could be perfectly a linear approximation. Something the same thing like this is a linear, could be a linear approximation. But if you have something like this, is not a linear approximation because it has a quadratic term, it's not a linear. So if they give you the choice to pick something that should be the linear approximation, make sure that it's always a line, never something different from a line. Okay, so you get something like this. It's not a linear approximation. Okay, in this scenario, you can see it here. Once that we define, okay, so we need f of a, f prime of a. So f of a is 2, and f prime, we can use the derivative of x to the 1/3, and it's going to be 1/3 x to the minus 2/3. And using that, I can get that f prime is 1/12. And so once that I replace that, I get this linear approximation 2 plus 1/12 x minus a. And then when I'm approximating, I can say, well, the square root of x, the cube root of x, sorry, is equals to more or less 2 plus 1/12 x minus 8. And so now I can actually plug that 8.2, and whatever this result is going to give me is going to be a very good approximation by the tangent line at that point. Okay. Don't forget to take a look at these exercises. This is something that for sure is going to come, and I'm going to be asking you to do one of this. Typical questions that you might expect tomorrow is, of course, you can expect one chain rule. You can expect one implicit differentiation. You can expect linearization. You can expect maximums and minimums in particular in an interval and outside of an interval in general. And of course, the application of that to optimizations, all the problems of optimization and related rates that can vary. There are multiple different things that can be put in that regard. So make sure to check all this type of problems for rate of change that I have available in here.
Okay.
All right. Okay, so my time is up for today, but make sure to check on the solutions that I'll be posting soon. And also make sure to check the worksheet solutions that I'll be posting tomorrow morning before the exam.
Okay.
All right. Thank you for coming and have a good day.
Thank you, you too.